Hi, I'm going to be speaking about data visualization in practice. In particular, I'm also be talking a lot about D3.js. And just to get a feel for the room, how many of you guys are front-end JavaScript developers? Raise your hand. OK, not as many as I thought there would be. OK, and how many of you have used D3.js before? OK, most of you guys, sweet. So what I'll do then is I will go through an introduction to D3.js, but I won't spend too much time there. I'll instead focus on the principles of data visualization. So my name is Rami, and I'm from Microsoft Canada, based out of Montreal. This is what I look like without a beard, hence why I have a beard now. And essentially, my job is to work with developers, startups, whoever it may be that are looking to build technology on top of our platform, whether it's Azure, Windows phones, web, open source technologies, whatever it is. And I'm here to help you guys out if you have any trouble with any of our platform, or if you've just got general questions that you want to ask about different web and open source technologies. I'm a web developer myself. Node.js, JavaScript is my bread and butter, so I'll be happy to answer any questions about those technologies if you have any. My Twitter is the best way to reach out to me, and would love to hear some feedback of this talk as it goes on. So I guess we should start with what is data visualization. I mean, it's a fairly easy to understand or define couple of words, right? Like it's like data visualization. It's really hard to not get it right away. But like if you really wanted a dictionary definition, I guess you could say that data visualization helps people understand data through visual display. Haha. But a more interesting question, I think, is why we do data visualization. And I would boil it down to essentially two things. One is communicating knowledge clearly and efficiently. And the other thing is displaying data to understand cause and effect. So in other words, there's sort of two reasons why we're doing this. One is to actually show and share knowledge that we already know about some type of data. And then the other one is to understand the data itself by displaying it visually so that we like notice patterns or sort of understand the cause and effect that might be taking place in the data. So there's really two reasons. So just to give you an example of what it is that I'm talking about, here's an example of a data visualization. It's Hubcap. It's a interactive visualization tool, and it essentially shows you all the taxi pickup points and the taxi drop-off points in New York City. So if you take a look at that, this is lots of data, as you can imagine, geographic data. But it's been visualized over a map, so it gives you a sense of where things are going and where the movements are between the pickup points and the drop-off points. So it's interesting that like Manhattan has way more yellow points, and Brooklyn has way more blue points. That could give you an idea of how the movement of people in New York City goes. And here's another one, another example. I really like this one because I'm a bit of a hipster and I love Brooklyn. So here's an example of essentially the age of every single building in Brooklyn, colored by how old it is and how young it is. So the bluer the color, the closer to blue, the older it is, and red is the newer buildings. And it sort of highlights where a lot of the redevelopment of Brooklyn has sort of been taking place. So if any of you have been to Brooklyn, you might recognize the Dumbo Bridge. Sort of the Dumbo area is all red, and that's because it's all basically new development. And it's really interesting. Had we shown this as sort of like a list or a table of like, oh, here are places where buildings were built, it would not really show you what neighborhoods are growing or what neighborhoods are sort of being rebuilt in Brooklyn as a visualization like this does. Now, all of these visualizations have been built with D3.js, but I just wanted to point one thing out. You don't have to build just graphs and maps with D3.js. You can actually build lots of really cool stuff, including shooter games. So when you think of D3.js, and I'll explain it in a couple of minutes, you'll see that you can apply this methodology, this way of thinking and manipulating data to also creating video games or pretty much anything that is interactive or data-driven. Now, of course, no talk about data visualization can't have a slide, can't have a slide without Edward Tufte. So here's mine. Edward Tufte, for those of you who don't know, is, I guess you can consider him one of the grandfathers of data visualization. He's been doing this for much longer than I've been alive. And his books have sort of become a classic. And the one that's on this slide is actually a really interesting one. It's essentially, if you take a look at this, it looks like a graph, like there's some flow of things going on, really. But this data visualization was actually the march of Napoleon's soldiers to Russia, and how many people actually ended up in Russia towards the end. So it's a sort of I would say like a data visualization specifically to the data set. It's meant to really illustrate the point of the sort of slow decline of the Grand Army as they approached Russia due to the winters that it encountered. So it was a really interesting data visualization that you can't really quite show in a single line graph, number of soldiers in the march as time passed on. It's a lot more clearer when you display it in this way. And then we'll get to this point about how do you actually display data in an interesting way as we talk through some of the principles of data visualizations. Now, another interesting question is, what is not data visualization? So I'm sorry to disappoint a lot of folks generally. Data visualization is not about making pretty things. It's not about aesthetics. It's really about insight. So if you ever get a marketer that comes up to you and says, hey, we need you to make us an infographic from this database, what you do is you say no, and then you just point them to my Twitter handle, and you say, go argue with Rami. He'll tell you not to do it. I'm willing to take the fight if that ever happens to you. Now, if you're wondering, like, why should I care about all this stuff? Why am I in this room? It's really because of this sort of trend that we're seeing in our industry of data collection and just the whole big data aspect of our lives, really. I mean, data is being collected everywhere. IoT devices are exploding. Your smartphone generates so much data a day that it's like, you can consider it a very, very active device, even if you're not using it. So with all this data that's happening, we really need to start caring a little bit more about data visualization. We can't just get away with having simple graphs and pie charts, because the data is a lot more complex than that. And the amount of data that we're collecting and the correlations that you could sort of discover between different data sets, it's huge. And that's really why you'll notice the data visualization in the past 4 or 5 years has had a bit of a resurgence. It's becoming more and more prevalent, especially in the fields of journalism, media. Data journalism is now one of the biggest things that you could be doing. So data visualization is an integral part of that. And you can sort of point to this beginning as point to big data as sort of the beginning of this revitalization of data visualization as sort of a thing that you do, or that you can be doing if you wanted to. So let's get started a bit about data visualization in practice with D3. I'm going to do first a 5-minute introduction to D3.js. I'm just going to run you through it. Most of you guys, I would say most of you guys are JavaScript developers, either back-end or front-end. Or raise your hand if you're a JavaScript developer. OK. Everyone? OK, so hopefully you'll be able to follow through if you're not a JavaScript developer. It should be all right. So what is D3.js? D3 is basically data-driven documents. There's an N that's missing in that first bullet. It's an open source JavaScript library for manipulating documents based on data. And D3 does 3 things really, 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 really well. One is it loads data from JSON, XML, CSV, TSVs, topo.json. That last one is really interesting because that's geographic coordinates and geographic data. So it does that all really well. The other thing that it does really well is it gives you lots of tools for selecting and manipulating elements, as well as binding these elements that you've selected to actual data points, so that when data points change, so do your elements, or at least there is some connection between the two. And the other thing that it does really well, sort of the last thing that I'm gonna mention, is that it makes transitioning elements between different states, whether they're data points between one number to another, really easily. So you can do some really nice interpolations between data points that are changing and have nice transitions and animations, as opposed to just doing a refresh and with a whole different graph. So that transition capability also is what lets you do real-time visualizations as well. So as more data comes in, you're able to manipulate elements and transition elements in a way that's very easy. So D3.js, you use it to transform HTML and SVG, so you can use it for both. So if you wanted to do some very if you're an SVG artist and you want to do some really fun stuff with SVG, you can. But most of us, I think, will probably use it for HTML manipulation. Now, if you're wondering, well, how do I load data from JSON, XML, and all these other variety of formats? It's really simple. You just call the function. Some of the simplicity of D3. It's a really simple framework. There's no setup that you need to do. You just call a function, and then you can chain function calls together. It takes a very declarative approach. Now, if you're wondering, OK, well, how do I select and manipulate elements and bind data to them? As I mentioned, D3 has a very declarative approach. So if you've ever used jQuery or a library like jQuery, okay, you'll sort of notice that pattern. You'll be able to sort of chain your functions and be able to apply things on roughly the same thing. So to select all the paragraph tags in a document, for example, you would just go D3 select all, and then you could style all of these paragraphs that you've selected by just chaining a style function to that. So it's very similar to jQuery. You might already be comfortable with this. And the other, like if you want to just select one thing, you can just do a select. Now, this is all interesting, but it has nothing to do with data. It's just selecting and manipulating elements. It gets more interesting when we start applying data to these elements that we've selected. So D3 lets you bind these elements using two functions, enter and exit. And essentially, the way it works is after you've selected whatever element that you want to attach data to, you call data with the data that you want to attach to these elements. So it could be an array of whatever. And then you call the enter function. Now, the enter function will then do something for every single like point in your data set. And in this case, we're just going to create a new paragraph, add some text to that paragraph that basically returns the number that was in that element. Now, all of a sudden, we've actually bound some HTML elements to actual data, and as the data change, so will the HTML elements change. And that's really the basis of actually creating other things in your visualization. And I'll actually run you a little bit of more complex example and show you how this binding actually takes place and ends up letting us create things like line graphs or charts or whatever. The other thing that I mentioned earlier is that the transitioning of elements between states is really easy. So D3 comes with some built-in interpolator functions that lets you interpolate numbers like from 0 to 100 and be able to do multiple events based off those interpolations. It also works with colors and compound values and even events inside, like even numbers inside strings. So here's an example of D3. When you select the body and then you start the transition, you can style that transition to become background color black. But whatever is its current background color, it will interpolate the colors that will take you from whatever that color is to black, so that you end up with this nice transition to that color, as opposed to it's now just changing it right off the bat. So I'm just going to run you through a demo for how to actually create a line chart. It's very simple and straightforward. Once you sort of frame D3 as this library that helps you select, manipulate, and then bind data to elements. If you wanted to check out this demo, it's actually on blocks.org. It's not actually blocks, it's bl.ocks.org. Great resource for lots of D3.js code. I'm going to flip out of my PowerPoint and open up Visual Studio Code and show you my index.html. So here's an example of basically an HTML file. Can you guys read this, or should I zoom in? Should I be zooming in? OK. OK, is that more readable? Yeah? OK, great. All right, so this is fairly straightforward. It's just some the HTML start stuff. And here we've got a couple of styling. The styling will come in handy later. You can just ignore it for now. First thing I do is obviously add in D3. And then I'm going to create a couple of things. I'm going to create a margin, and I'm going to give it, for my graph, I'm going to give it a margin, give it a width and a height. And then from there, I'm going to create this function that knows how to parse one of my times formats. So D3 comes with these formatting tools that you could use and data manipulation tools, like functions that you could use. So if you're just building visualizations, you can stick to D3. You don't need any other library for a lot of things. You can just use D3's functions. And then what D3 also lets me do when it comes to time is create these scales so that I can create this a scale that basically gives me a range of some date. So if I wanted to go from 1990 to 2000, I can create a scale that gives me 1990, 1991, 1992, and all of that stuff. So you don't have to do that manually. You can also create scales that are just linear. The next thing I'm going to do is I'm going to create this axis. Now, because D3 is so commonly used with data visualization, it comes with some extra tools that sort of make it very easy for you to create visualizations like charts and stuff. So axis is one of them. It lets you create this like a simple function, just create an axis. So here's what it does: d3.svg, call the axis function, say that the scale is x, in other words, some time scale, and then orient it to the bottom. For the y-axis, we're going to do roughly the same thing. Okay, and then what I'm going to do is I'm going to create a line. Okay, because a line is part of our line chart. And then for when I call d3.svg.line, for the x, I'm going to say I'm going to give it this function that just does something with the date of my data element. Okay, so it'll return x with the date, and then y, it'll return the y with the close, which was sort of the closing price of my line chart. Now here's where we sort of are reminded of this whole selecting piece. What I'm going to do is I'm going to select the body, I'm going to append an SVG sort of element. From there, I'm going to give it some width and height attribute. And then I'm going to append G, which in SVG terms is just something that fits inside the SVG. And then I'm going to transform this by giving it a translate. Okay. This is fairly like replaceable. You can replace this with HTML. It's not particularly important. SVG is a little bit more flexible in this case because we're drawing lines. So in cases where you don't want to draw lines, you just want to bind it to elements, you just use HTML. So as I mentioned earlier, it's really easy to load data. So here we have a TSV file, which is basically a tab-separated values file. If you want to take a look at what it looks like, this is essentially it. It's a date and a closing price for something. Okay, we're not putting anything right now, but that's what it is. If I go back here, just by calling the TSV function, I'm able to pass in the name of the file, and it's going to load the data. Pass in this callback that for every single data, we're going to do the parse of the date. And then we're going to match the X domain with the data so that it's returning the actual date. And from there, we're going to append a G that basically gives it the X-axis, and then another G that gives it the Y-axis, and then add the text that basically sits there. And then finally append the path, which is the line that we created right up here. So roughly under 100 lines of code. And you basically will end up with something like this. I'm just going to open up my command prompt so I can create a simple HTTP server. I'm going to go in here. Great. Open up my browser. That's essentially it. So this is going to read the data and basically spit out that line. Here's that x-axis. Here's that y-axis. So you'll notice the dates, the y-axis, and the values on the x-axis. And that's pretty much it. It's going to map the x and y coordinates of the lines with the date and the close number in our file. Sounds good? Okay, these samples are all available online, so it might be a lot to take in at one moment, but that's roughly how D3 works. And if you need some more time, we can go back to this example a little later. Okay, great. So now that we've sort of seen a sort of rough introduction, 5-minute introduction to how D3 actually works, let's talk a little bit about the sort of principles that you might need for creating good data visualizations. And the first principle I really want to share is that context is king. The context in which data is visually placed sort of impacts the knowledge that you can communicate. So where you put that data, what context it's in, how that data is placed really has an effect. And just to give you an example, so to make this more clear, any of you guys heard of Stop-and-Frisk in New York City? Yeah? Okay. Essentially, it was this controversial policing tactic that involved stopping people in the street who the police deemed that might be suspicious, and then frisking them. So what was interesting, though, is that the police actually compiled really detailed data about all of their activities. So that was interesting, because then we could sort of plot and discover things about what was happening in the New York City stop and frisk, like stuff, like what they were doing, and sort of get some information that the police department wouldn't say, for example. So let me give you an example. Let's say that we took all this data. It included things like, okay, well, geographic information, like where we did this stop, and then also what time. All right. So if we just took this data, very simple data, and just plotted it on a graph, you'd get something like this, right? You can see the stops by week over the number of years that this was in place. Obviously, there's some really interesting spikes. Like for some reason, earlier in the years, there's more stops by week. Maybe there's some quota or something that they're trying to fill. Then towards the end of the year, right? Interesting. But like not a lot of really like powerful information that we can get out of this, right? But like if we took the same data set and instead mapped it on, say, a map, then we could see, okay, well, this is where all of the data, like the stop and frisk situations were happening, right? So if we just put a dot for every single place that it did, you'll notice that there's a very easy pattern that we can see here. Brooklyn around here had way more stops and frisks, and so did Manhattan downtown and up here towards the Bronx area than elsewhere. Wonder why? It's interesting. But now, if we just put all this data on a map, right, we sort of lose that temporal, that sort of temporal property that we had, because our first graph had this whole time bar at the bottom. When we just put everything on a map, we sort of lose that. One way that we could sort of fix that and fix the context is by having perhaps two. Here's an example of the first half of 2012, when this policy was still in effect, and then the last half of 2013 after it had stopped. All right, but for some reason it had stopped in places where it was very visible, so like Manhattan and some of the other areas. Okay, like over here, but it was still going on in other places, right? Just far away from where journalists would see this or when people were complaining. Okay, so interesting. That's something that we couldn't have gotten just by looking at either maps, like the map or the graph that we had before, right? Because we wouldn't have noticed any of these patterns at all. And here's another interesting thing that the New York City police had done, is that they had also collected the race of the people that they were stopping. So again, that gives us a lot more information about what's actually happening, and how there in some neighborhoods there was more of one like sort of the blue color and then the orange color more than some of the other colors that were out there overall. So there's a lot more data that we can sort of get just by simply placing putting the context of where these things are. And if you wanted to learn more about this, my slides are already online on SlideShare, and you can actually go to the article and learn more about all these different situations. Another example of sort of the context is king idea is that how you sort of display your data, the context that you put them in, gives you a very, can influence what information you actually learn from the graph. So looking at this graph, this map. This map basically colors the state by where they sit on the poverty scales. Okay, like how many people are under the poverty line in each scale, in each state. If you color it in this way, this is taken from one of the Guardian's blogs, the data blog that they have. It looks like, okay, it seems like the more south you get, generally the more people under the poverty line in those states, right? Okay. But this is, if you look at this, like the context that this is placed in, they were trying to make a point, but if you actually look at the data, you'll notice that the Guardian had done some really interesting stuff. One, they had messed around with the class limits. So what they considered to sort of fit into this more like larger proportion of poor people in that state, they had sort of skewed the lines. So if you took a look at all of the data, the state with the least poverty had 6.6% of people under the poverty line, and the state with most had 22.7. Now, if you sort of took this range and decided I'm going to split it equally, and then color every state based off where they would fit, you would end up with like class limits that look like this, right? 6.6 to 9.8 to 13 to 16.3, something like that, right? What the Guardian had actually done is they had messed around with the class number, so all of a sudden, for some values they had rounded up, and then for some values they had rounded down. And then what ended up happening was more states fell into the darker area at the bottom than if they had used a sort of equidistant categories. And the difference can be very profound. All right. And the other thing that you want to note is that just using your colors also will change the context. So here's two examples, two color schemes. Okay. Just give me just raise your hands if you feel that you can differentiate between the poorer states and the less poor states better in this graph up here than in this one. So if you think this one is more clear, raise your hand. Pretty much everyone, right? And that's because the colors that they had used, sort of that context that they had placed this data in, the spectrum was designed in a way that like the hues between the most poorer states was less visible than if they had used colors that were significantly different from here to here to this one than if they had just placed it like this. Actually, what's funny is that if they had just taken this spectrum and just flipped the order and mapped it to the other way around, it would have been a lot more clear, which is interesting. But anyways, again, the context that you place your data in and the visualization in will have a big effect of what people actually learn from these things. Because if you had taken a look at just this part right here, you would have noticed that it seems like everything that gets closer to the south is poorer, when in fact, really it was like mostly just Mississippi and Alabama that had like, or I think that's Alabama, but anyways, I don't really know my states very well. But just this area, this part next to the Mississippi River, that was significantly poorer than everything else. And it's a lot clearer that way. So if you place data in comparison, like for context, it's very important. Here's a little GIF that shows you, like if just changing the number of classes that you have, like the categories, the counts, completely like changes what you understand from your graph. So looking at like 2 classes, then it's really hard to understand or see anything. Around classes like 6, number of classes of 6, data becomes less clear because there's just too much going on. You can't quite differentiate between the colors anymore. Now, if you're wondering, okay, well, how do I do this all with D3.js? The nice thing about D3.js is that it includes routines for handling geographic information. If you don't know, GeoJSON is sort of the geographic data file of choice. It's what most people use to represent maps. GeoJSON is great, but I actually like TopoJSON a lot more. It's an extension of GeoJSON. What it does, though, instead is when you have states that are connected together, like here, for example, GeoJSON will show that, like, will write the boundaries of both states, even though they are intersecting or like they're the same boundaries in the same file. TopoJSON removes the duplication, so you end up with way smaller files, especially when you're trying to get a map of like every single county of the states, or for example, or something like that. Now, if you wonder where do I actually get these files, Mike Bostock, who's the creator of D3.js, has 2 repositories on GitHub that give you an atlas of the world and the US. The US one is very, very detailed. It goes all the way down to county level, so you can see like the counties in the states, which is really useful. If you want to see some demos, I actually have a few. Here's an example of coloring the counties. So he's using a log scale from red to blue, which makes it really, really clear. And the color is based off how big that county is. Right? So the bluer the parts of the states are, the bigger the counties are, versus the deeper reds that you get, the smaller the counties are. It's pretty fun. Here's another example. This is just chopo.json. This is a single file that gives you all this information. So just sort of to wrap up this section, context. The context in which data is visually placed sort of impacts that knowledge you can understand. So you want to make sure that you're enforcing the right comparisons for the context. And the other thing is that many problems are sort of multivariate. They have multiple variables. And that needs to be recognized in your data visualization. You can't just reduce data that could be very complex to just a 2-dimensional, 2-scale solution. The second principle that I sort of want to share is that it might sound really, really obvious, but it's really important. The visualizations must match the data. Right? That sounds like very obvious. But really what I'm trying to say is you can sort of use data visualization to sort of mask, cheat, and lie. Because that's, like, don't do that. Here's some example of how you could do that, though. But don't tell anyone that you learned this from me. So one of the although it sounds like a fairly obvious point, a lot of people actually miss this. Here's an example of how you can lie with data visualization. Let's say that you are measuring like the increases of interest rates. Okay, interest rates generally, if your problem domain had very small increments, your y-axis has a big effect of like how much differences that a user will perceive, right? So on this side right here. The y-axis is very, 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 very detailed. So it starts from 3.140 and goes all the way up to 3.152. And the differences between that, like in the interest rates that they were trying to show, they're very, very small increments. But this graph seems to imply that they're huge increases, right? Versus if you had just mapped it to like 0.5 increments, where it seems like the interest rates has only been increasing very slightly, right? It really depends on what you're trying to show, right? But if you were trying to make the point that, the interest rates are increasing dramatically when it's just very, very, very small increments, well, then you could just show this graph versus this one, which actually shows you a little bit something closer to truth, depending on what you're trying to show. Here's a really interesting one that I really like. It's the difference between cumulative annual revenue and annual revenue. So let's say that you're a company and you're not doing very well. So instead of just showing the annual revenue, let's just show everything that we've done in the past and then whatever we've added this year. That's the difference between cumulative revenue and annual revenue. And here, it shows vastly different graphs, right? Like cumulative annual revenue will show that, it seems like we're always making more money, right? For someone who's just looking at this data really quickly, they might not notice your title, or you can just obscure the title away if you had done that, versus annual revenue that was actually showing you a very big decline in revenue that was taking place. Here's another example. I really like this one because it's very creative, and essentially this was a cause for a lawsuit in the States at one point. Essentially, this company knew that their quarterly revenue wasn't doing particularly well, right? Like it was constantly going up and down. So what they wanted to show was that they were a much more stable company. So instead of showing quarterly revenue in a graph, they decided we're going to show it by fiscal year. Okay, so all of a sudden it looks slightly better, right? But there's still this huge dip in 1982 that takes place. Okay. But then, if you really were, because they were super creative here, instead of actually using the revenue by fiscal year, which is what you're supposed to be doing, they're like, okay, no, let's time shift everything to calendar year, and that actually will give us a nicer graph, because we're mixing in two different fiscal years where one was better and one wasn't, and it shows a way better revenue stream, right? So, okay. I'm not going to demo cross-filter because I realize that I'm slowly running out of time. But this is a great library if you want to use. It's built on top of D3.js and lets you explore multiple variable data sets and sort of filter things and see what the impacts would be. And it's really, really fast. So definitely check it out. So anyways, don't use visualizations to lie and cheat, please. And if you do, don't blame me. Don't say I told you so or told you how to do it. But really what I'm trying to say is that the knowledge that you're sort of showing in a data visualization should actually match the data, and you should not be using visualizations to sort of obscure things or make things less clear. And the other thing is follow convention in how you model your data and your axis. If your industry or field or whatever has a data axis that is in very small increments, like a y-axis small increments, you should probably be using that one than making your own that sort of obscures the point that you're or hides things. Okay, so it will not serve your purpose if you do that. The last principle that I'll probably sort of share with you today because I realize I'm running out of time, is that you can escape Flatland. So just because our screens are two-dimensional does not mean that our data also has to be two-dimensional. It sounds very obvious, but it can also lead to errors as well in how you visualize data. And let me just show you a good example. Here's one from the New York Times. You'll notice that I use a lot of New York Times examples, and that's because they're awesome at data visualization, and a lot of the developers are really good. So here's an example of how New York has been reshaped based off of Mr. Bloomberg's rezoning of different parts of the city, right? Now, if you had just put this on a 2D map, it wouldn't be very clear how that impacts the skyline and what people actually see in the city, right? So you can map this on a map and like put the places where the zones have been changed, but you wouldn't notice. But if you put it in 3D though, you'll actually see, okay, well in some parts of New York, the view has been dramatically changed. Okay, maybe not less here, but okay, well in pictures it actually does show quite a bit. But in other places, particularly in Brooklyn, where a lot of buildings were rezoned, that's huge, 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 huge amount of differences, right? So rezoning on a 2D map wouldn't have shown you this information. But if you put it in 3D, you'll notice, okay, well, that's going to vastly change the skyline, okay, of New York. Here's another great example from Paul Butler, who was an intern at Facebook when he did this. It's probably less clear on the screen, but it is three-dimensional. And it shows like a mapping of all the friends, like friend relationships that existed on Facebook at the time. And it's really interesting. You'll notice this huge gap in the world, and that's China, because China has banned Facebook. And you'll notice some other gaps around here and here, probably because it's mostly forests around here. But it's still pretty cool that you can see how like the sort of the world is sort of mapped all over the place. Another thing that you could use sort of 3 dimensions for is if you're showing like geographic information on a global scale. So like earthquakes have huge impact, and it's a global thing, so why not show 3 dimensions? Here's an example where 3 dimensions adds practically no value and just makes things a lot more complicated to understand. And yes, I know that it's interactive, but here's one where like, yes, like it's 3-dimensional and interactive, but it's like just looking at it is completely confusing. Each shape basically shows how one film did at the box office, but they've overlaid all the films on top of each other. So it just looks like I have no idea what's going on. Here's one that I thought was really weird, and I actually showed this to a comedian friend of mine, and he told me that like this looked like hair. But this is like every single year, the UK temperature history for every single year from 1911 to 1989. Yes, it's a 2-dimensional graph, then turned 3D, but it just obscures things and just like completely like it's useless. To me anyways. But yes, you can scroll between all the years, but as you scroll, you'll still see the other gray lines. So it doesn't actually provide any information, even though it is 3-dimensional. Principle 4. Aggregating details can reveal the knowledge present in data. This is really interesting. Basically what I'm trying to say is that if you take all of the data and then visualize all of it, that can give you interesting information that you can't see by just visualizing chunks of it. Right? So here's an example of house hunting all day, every day. That's what the name of the visualization is. It's by Trulia. So for those of you who don't know, it's a startup that does real estate stuff. And essentially, what it does is it shows you for the entire year when houses and house hunting is the most busy. So you'll notice that towards the end of the day, after 12 p.m. to about 7 p.m. is when house hunting traffic is the highest, right? And then it'll change depending on if it's the weekend, except for Sunday where it's just busy all day. Saturday, Friday, nothing going on. Wednesday and Thursday, interesting. Now this graph would have been is only possible when you take all of the data and merge it together, right? That's what I mean. Like aggregate all the data and put it in one place. You actually see something interesting versus if you had taken a look at it of like on per day, like where things like how much traffic was at what point of the day or not. The only other way to actually show this is if you had put 7 different lines for every single day, right? But it would have been unclear. This is a way nicer way to visualize this idea. Here's another example. If you guys are very interested in sorting algorithms, anyone? One person, 2 people, yes. Okay, so if you do shuffling, all right, how you compute random numbers is really important because that will help you shuffle things. Now, some ways to do it are better than others. So here's an example by Mike Bostock where he actually shows you like how some comparators are not very good because they basically give you a very positive bias for some type of numbers, okay? Versus other algorithms where if you, let's say, instead of using sort, you use like Fisher-Yates, they give you you are like less likely to be biased to a certain bunch of numbers than if you were using some of the other functions. If you were using, say, for example, a naive swap, for example, so the middle, like so when you have numbers that are roughly the same, will end up being a lot more have a bigger positive bias than other ones. Here's another one of life expectancy in the world. And it's for every single country that they have data for. So you can see how generally everywhere in the world, your life expectancy has been increasing. Obviously, some countries will have started higher up on that list, but roughly we're all sort of moving together upwards. And in some cases, you see a group of countries all of a sudden start lower and then catch up at the end. Right? So that's something that is really nice. Otherwise, the only way to represent this data otherwise is to just show it by country. But when you put them all together, you'll see how countries in general are moving higher and how some countries are catching up and other countries are sort of yo-yoing a bit. The last principle that I will share is sort of, I couldn't find a name for it, but basically I said insights from Hay Bales. That's how I sort of named it. And it's the idea of like layering and parallelizing some data visualizations can show you insights, but be careful not to form these big haystacks that are very messy. So if you know what a hay bale is, it looks like this. That's a haystack. That's a hay bale. So you can put visualizations together and stack them on top of each other, but if you do it in like a smart way, you can actually get these nice organized clumps as opposed to this big mess. Here's some ways that you could do that. Layering data that have a common x-axis, you can sort of maximize visualizations of coincidences and anomalies, and this is really useful for time series data. And then this is when you layer data on top of each other. When you parallelize data, it's basically very powerful when you're trying to show that there are big differences between multiple data sets. So if you're wondering what I'm talking about, here's an example. Here's basically 15 charts that show the effectiveness of birth control across different mechanisms. So you'll notice that like the dashed line is sort of perfect use versus a typical use. So you'll notice that some mechanisms are more effective than others, and then when. Now, if you had just put this all on top of each other, it wouldn't be very obvious, okay? Because the perfect uses, sort of the baselines are different for every single way that you could do that. But if you put them all next to each other and you sort of rank them by like which one's most effective, you'll actually be able to understand different things a little bit better. Here's another example where you're just putting stuff on top of each other. This is CPU usage across like a bunch of different servers. What this lets you do, though, if you just stack them all on top of each other, is when there are anomalies that are happening or when there are things that are very bizarre, you'll be able to see them quite clearly over a time series. So, and the other thing that you'll be able to notice is like rolling updates, for example. Let's say that you're running a bunch of tasks on all the servers sort of in sequence. This graph actually shows you that quite clearly. Like there's a bunch of places where there's more CPU usage, but it's all sort of in a rolling fashion, right? And then when you see anomalies, you'll actually know, okay, well, this is something weird that's happening, but in other places it's not. So that you can see sort of in aggregate by putting them on top of each other. Here's an example with networks. Here's something that you could do also, is if you change the time series that you're using, here's the network for every 10 seconds. Let's say that you collected that data over 5 minutes. You'll notice how in some place, like basically when the network activity diminishes is when it's the weekend versus the week. And you'll notice that there are some anomalies in some places where some things must have happened during the weekend. So it's easy to spot anomalies when you sort of put the data this way, but when you just have one graph for every single server, it's sort of not very useful. This is using Cubism. If you want to take a look at Cubism, you can just go to GitHub. There's an Intro to Cubism like PDF at GitHub. If you wanted some books about data visualization, anything by Edward Tufte is amazing. He has a bunch of books out there. He's a really great resource if you want to learn about data visualization, and if you just want to know about the history and some of the stuff that he's invented as well. Another great book is Knowledge/Information is Beautiful. And essentially, it's two different books, but the same is beautiful at the end. Both great books. Another one is Designing News by Franchi. It's another great book. If you want to go to a conference that's all about data visualization, Visualize in New York is pretty much that. It does a really nice job of like mixing storytelling, data, and engineering and art a bit together to get like a really fun, interesting conference. And then here are some websites in case you were wondering. Mike Bostock, the creator of D3.js, has awesome resources on blocks.org, and the D3.js gallery is full of examples of how to actually create multiple things. And why don't I just point you to it right now, just to show you. There's lots of stuff that you could create with D3.js. And they all use roughly the same idea of mapping elements to data points. Plenty of stuff. If you're looking for people to follow on Twitter, Edward Tufte, he's still alive and doing awesome stuff at Yale and Princeton. He's just at Edward Tufte. Mike Bostock, this is out of date. He's no longer the graphics editor at New York Times. Jonathan Coram does some really interesting stuff. Brett Victor and Gregor Aisch are really cool too. So essentially that's about it. What did we learn? Had a bit of an introduction to data visualization. Talked about some principles. So if you need to remember them, context is king. So how you place your data and what context you put it in will have a huge impact of what you can learn. Visualizations must match the data as well. Please don't cheat and lie with your visualizations. They have to match the data. You can escape Flatland when it's useful. I guess that's it. Thank you very much. And if you have any questions, I'll be happy to answer them. Thank you.